So yeah, so the theme of this talk is just exploring wallpaper groups through origami. So I guess, I mean, I'm an academic mathematician, but this kind of geometric origami is sort of a hobby of mine. And let me see, am I using the right camera actually? And so I just want to explain a little bit about exploring these wallpaper groups. So this connects a little bit to this morning's talk where Teresa was talking about the light on art forms, because these are all, each one of these patterns is a single sheet of paper, but it's just tacked onto a window and the light is shining through from behind. And so this one, for example, is all yellow paper, but the differences in colors just come from different thicknesses of paper where the folds are. So where the darkest points are, maybe there are 3 or 4 layers, and where the lightest points are, there's only 1 layer. And by putting these pictures up on a window, you can really see the details of the pattern. So these are 4 different so-called wallpaper patterns, which I'll mention during this talk, explain how they're related to each other, how they're different from each other, and how we can try to move between them using origami. So let me just plug that one so that. Okay, so just to say a few words, first of all, about the mathematical concept of the wallpaper groups. So wallpaper groups classify the distinct systems of symmetries that can occur in a periodic tiling of 2-dimensional space. So basically think of a tiling of a floor or a wall. There are 17 different wallpaper groups, so there are 17 sort of structurally different patterns that can occur. All of them have the property that there's a basic tile that covers the plane without overlaps and without intersections. And so all of them have, amongst all the symmetries that are involved, to have translational symmetries in 2 independent directions, coming from just sliding the basic tile along some directions of symmetry. They may also have rotational symmetries, and they may have reflections. So rotations, if they occur, can only occur through of order 1, which would be a rotation through 0 degrees, 2, which would be a rotation through 180, 3, 4, or 6. And this is the famous crystallographic restriction, which tells us what the basic angles of rotation can be in a periodic tiling of the plane. So a primitive cell is a minimal tile that generates the whole pattern through its translations. So for example, in this picture, there's an example of a primitive cell. So if we take this particular square, this is an origami tessellation. If we take that square and slide it along, we can cover the next copy would be here, there'd be a copy here and here, and we can cover the entire plane with just translated copies of this primitive cell. Okay, and there's no smaller version of that one, there's no subset of that cell that will do the same trick if we only allow ourselves to use translations. So a fundamental domain then is a minimal region that would generate the whole pattern by taking its images under all symmetries of the whole periodic tiling, not necessarily only translations, but also, for example, reflections and rotations. So in this particular example, if we take this little triangle, we can see that we have the full symmetry of the square here is exhibited in this tiling. So if we take that little triangle, we can do a reflection, for example, in this vertical axis. That's a reflection of the entire pattern that would fill in this square for us, and then we can use the rotations around the center of the primitive cell maybe to fill up the rest of the tile. So this little triangle, if we allow ourselves to apply all reflections and rotations to it, as well as translations, would actually generate the entire pattern. But if we only allow ourselves to use the translations, then this lighted colored square will do it. So I want to talk about realizing a few of these wallpaper groups through origami. I won't talk about all 17 of them. And the reason why the 3 and 6 are highlighted here amongst the rotation orders is because I'm actually going to talk about the ones that have rotational symmetries, either of order 6, so a rotation through 60 degrees, or of order 3, so a rotation through 120 degrees. And I guess I find these wallpaper patterns really fascinating because they exist in mathematics, of course, and they also have a life in the decorative arts that goes back through millennia, and that they've been independently discovered and enjoyed by people throughout the millennia, and they appear in design and in art throughout history. And so I won't talk about all 17 of them, but we'll talk about 5 of them in particular, and those are the 5 that have rotationals of order 6 and order 3. So this talk, I hope it'll be okay. It's going to be it's going to move between slides and sort of an attempt to do something live. So we'll see how that works out. So, okay. So we're going to think first of all, so I suppose next step, I want to try to kind of explain where the wallpaper groups that have, where the wallpaper patterns that have rotational symmetries to 60 degrees, so 6-fold rotations, how they arise and where they come from, and how we can kind of figure out what their structural symmetries must look like, even if we can't figure out exactly what the pattern itself must look like as a sort of visual when you first see it. So all this, all the patterns with 6-fold rotations have something in common, sort of at the structural level, but they may not resemble each other that much when you see them. Okay, so we're going to suppose that this is our plane, and we're going to create the structural geometry of a pattern with 6-fold rotation. And this blue dot is going to be a center of 6-fold rotational symmetry. So the whole picture is going to be symmetric by a rotation to 60 degrees about this point. And because we're talking about a periodic pattern, there have to be other 6-fold centers of symmetry. So let's let this red one be a center of 6-fold symmetry in such a way that the distance between these two is as small as it can be for a pair of 6-fold rotation centers. Okay, well then if we rotate this one, if we rotate through 60 degrees around the blue one, we get more centers of 6-fold rotational symmetry, which must look like that. And if we rotate around all of those, the image of this blue one under rotation about any of these red ones, through 60, 120, and so on, must be another center of 6-fold rotational symmetry. So we find that the centers of 6-fold symmetry have to form, they must form this sort of triangular lattice formation. Okay, and moreover, there can't be any more of them because we agreed that the first pair should be as close together as 2 centers of 6-fold rotational symmetry can be in this picture. Okay, so if we fill in some sort of tiles between these dots, these centers of 6-fold rotational symmetry, we get a picture like this. They're written in 2 colors because there are basically sort of 2 types of triangles here. There's a triangle that points upwards from this blue one points up from a horizontal base, and there's this white one which sort of points down from a base up there. So the blue triangles and the white triangles are oppositely oriented. And I'm not saying that the overall picture has to look like a sort of triangular pattern of tiles like this. I'm saying that the centers of 6-fold rotational symmetry have to have this sort of formation. Okay, so these tiles, we can imagine them as being decorated. They don't even have to be triangular, but they have to have sort of the symmetry of a triangle. So they might be decorated in different ways. So we can say, for example, that this blue vertex is a center of 6-fold symmetry. So the white triangle here must be an image of the blue one under a rotation through 60 degrees around this point, equally around this point. And by composing pairs of these rotations together, we can observe that, for example, as a composition of these rotations through 60 degrees, we can translate this blue triangle onto that one and subsequently onto any other one. And also, by composing these rotations, we can achieve a rotation through a 3-fold rotation, a rotation through 120 degrees of any one of these triangles around its center. So the centers of all of these blue and white triangles must be 3-fold rotational symmetry centers of the whole pattern. So we've got all that sort of rotational symmetry built in. And in particular, all the blue triangles must be translates of each other, and all the white triangles must be translates of each other. And so, for example, a primitive cell in this picture would consist of a blue triangle and a white triangle like this. Not necessarily in that orientation, but that would be an example of a primitive cell. All the copies of that rhombus have to be translates of each other, and those, of course, fill the whole picture. For a fundamental domain here, we know that we have 3-fold symmetry around the center of each triangle and 6-fold symmetry around all the vertices. So at worst, this region, through its images under rotational symmetry, for example, about this point, and indeed about that one through 60 degrees, or 120 about this one, will fill the primitive cell and subsequently all the domain. But it could be that there is more symmetry than that in the picture. For example, it could be that the designs of the tiles are such that the reflectional symmetries of the triangles, so for example, through these axes that pass through a vertex and the midpoint of an opposite side, there could be reflections of these lines that could be symmetries of the pattern. So returning to origami, I'd like to give a couple of examples of the kinds of things that could happen. So these are 2 origami pictures. They're 2 origami foldings. They resemble each other closely, and they kind of exhibit the 2 things that can happen in a wallpaper pattern with 6-fold rotational symmetry. So if we look at them, we can see that, yeah, there's some resemblance. For example, both of them have these kind of hexagons in the same places. And both of them have these kind of three-pointed sort of little patterns, these little three-pointed shapes, and they occur in the same places as well. But apart from that, they don't look the same. The yellow one has these sort of double diamond things. The blue one doesn't have those, but it has these little kind of diamonds kind of scattered around in a circle. So the difference between these two patterns from the wallpaper group point of view is that the yellow one, the one on the left, has reflections, and the blue one doesn't. In terms of primitive cells, so the triangles that we talked about in the last slide, the centers of six-fold rotational symmetry are the centers of these hexagons. And then so they make these triangles, like that one. And at the center of each of those triangles is a center of threefold rotational symmetry of the whole pattern. That's true in both pictures. The fundamental domain, just as we saw in the sort of generic diagram, is exhibited by both of these sort of lighted rhombuses. But the difference between the symmetry structure of the two patterns is that the one on the left also has these reflectional symmetries in all of these axes. It has all the full symmetry of the equilateral triangle. So all of these lines and all of their translates are axes of reflection in the picture on the left. So this one represents the group which is called P6M, which is, the P6 stands for rotation of order 6, and the M stands for mirror, because it has axes of mirror symmetry, as well as the rotational axes. And the one on the left doesn't have these mirrors, it just has the rotations. So if it's okay, I'd like to try to explain a little bit about how to create these patterns from origami, and also how to relate the two of them to each other. So I suppose I should say maybe, what I'm trying to get at here is the idea that you could create an origami pattern with folded paper that can be sort of adjusted from one wallpaper pattern to another by making relatively minor adjustments that really sort of highlight how by adjusting some folds, you can knock out the reflectional symmetry, or you could knock out the six-fold rotations, for example, and keep the three-fold rotations, and what you have to do and how much kind of variation you have in your hands if you want to do it. So at this point, if it's okay, I'm going to stop sharing this one. I'll come back to it shortly. And I want to explain something as well about the words in the slide here, the pre-creased triangular grid and the triangle twists and pleat intersections. So a couple of origami techniques coming up here. So I'm going to stop sharing that. I hope that you'll be able to see my camera if I turn it on. I can't see it myself. Can you see a sheet of paper here in the camera? Excellent, great.
Yes.
So what I mean by a six-fold rotational, a pre-creased triangular grid is basically this. So it's a square of paper, and it's just folded into a pattern that has all these equilateral triangles. And so I suppose the first step in creating these designs is to do the pre-creasing, to fold the triangular grid on the piece of paper. That's a step that I guess it's kind of the tedious step, and certainly not the most fun one, but it's really important to do it accurately because problems at this step will cost you later. A triangle twist, well actually a pleat intersection first. So a pleat is just pick up a fold like this, fold it over, so you create a sort of heavier band where the pleat is. And a pleat intersection is what you get if you just intersect three of those pleats at a point. So can you see what I'm doing here? I'm really sorry, I can't see it myself. So it's, yeah, okay, great, thanks, Melina. I can see you. Okay, so that's a pleat intersection. And so it creates obviously the bands of light and dark. And then a triangle twist is my absolute favorite thing in origami. So if you pick up the pleats in a pleat intersection like that and just sort of hold down the centers, the corners of the triangle like this, you can just sort of press down the corners with a bit of tension on the triangle, and it will actually fold down into a triangle like that. And those are the sort of basic steps that are involved in all of these designs. Okay, now I can see it, that's better. Okay, so that's a triangle twist and a pleat intersection. And honestly, I mean, I spend my time doing triangle twists when I'm having a bad day because I just love it. And I think that, you know, paper is this is one of the things I wanted to say too. Paper is just an amazing material, in my opinion. It's, you know, it's so familiar to us and it's such an everyday material that we can forget how special it is. It has these wonderful properties. It's pliable, but it's quite strong. It's quite tensile. It's pliable, and it can be flattened, and it can be rolled, it can be folded, and it can be unfolded. Like, how many materials can be folded and unfolded, but still retain a memory of the crease? So, you know, you could, so paper is just wonderful, and it has this wonderful sort of idea that, you know, it's kind of just pliable enough that it can withhold tension, stay sort of controlled, and you can press down this triangle. There are I mean, I don't think there are many fabrics really that you can do that with. So paper is special. There are things that are special like water and paper and cubes that are so unique and so familiar that we can sometimes forget how miraculous they are. That's my first comment. Okay, so the triangle twist and pleat intersections. Okay, so let me show you another one. So this is a copy of the yellow picture. And can I zoom in a little bit? Okay, can I maybe reduce the light a little bit? Okay, so it's not the full picture, but it's a partial version of it. And I suppose if you want to ask ourselves, how can we go from this picture, which has all the reflections, as well as all the six-fold rotations, to a version that just has the six-fold rotations? And I guess if we look at this, we can say, okay, well, we talked about the fundamental or the primitive cell in terms of a rhombus, but we have these hexagons. And the picture has the full symmetry of these hexagons, all the six reflections, as well as the rotations. So if we wanted to kind of knock out the reflections, but keep the rotations, you know, what could we do? And this is another wonderful thing about paper. I mean, of course, you can do this with a drawing, or with a, you know, but you'd have to sort of do a different drawing for the next version. With paper, we can just adjust some of the folds that we made. So looking at this one, the little light points here are kind of in the center of the sides of the hexagons. But if we can just adjust these folds so they're moved sideways a bit, so that they don't live at the center anymore. Then suddenly we've replaced our fully symmetric hexagon with a version that still has the rotational symmetries, but doesn't have the reflections anymore. And so we can do this all around the entire tessellation. And we've transformed the yellow picture on the left, which was the one for the group P6M, to the one on the right, which was for the group P6, which only has the rotations and doesn't have all the reflections anymore. So I suppose what I'm kind of trying to do is come up with as few as possible origami tessellations that look nice, but that can, through relatively minor adjustments, give us all 17 wallpaper patterns. And so you can't do it with just one, because, you know, some of them rely on a sort of square lattice, and some of them rely on this kind of triangular lattice. But you can do quite a lot with relatively few kind of basic patterns. And I also find it sort of fascinating to just see how the pictures change when they're backlit, when you make a few sort of relatively small adjustments. So yeah, so you can move between P6M and P6 on this picture by adjusting all those folds. So maybe I'll just say a few more words. I know that we don't have a huge amount of time, and I'm getting towards the end of my 20 minutes, but I'm going to return now to the slides, if that's okay, and just say a few words about some more examples of wallpaper groups of which have a threefold symmetry. So those are P6M and P6. Okay, so supposing then that we had a threefold rotation in our wallpaper pattern, but not a sixfold rotation. Okay, so if we can do the same trick. We can start with a threefold rotation center, call it the origin, and its image this time under a shortest rotation, not necessarily the nearest other threefold rotation center. But let's say this red one is an image of the blue one under a shortest translation of the whole picture. Then, okay, so the blue one is a threefold rotation center. So these two also must be threefold rotation centers. But that means since the vector that goes from the blue one to this red one is a translation, the other two must be as well. And that means that their negatives are too. So we have this picture of threefold rotation centers, all of which also represent translations. Once we do that, we can extend them and get, again, a triangular lattice. And again, we can fill that up with triangles. Oops, okay. But the difference here is that we don't imagine that we have sixfold symmetry anymore. We don't know what decorations are in these triangles, the yellow ones and the white ones. We know that all the yellow ones are images of each other under translations, and that all the vertices are centers of threefold symmetry, but not sixfold. So the yellow one and the white one are not images of each other under a rotation around the blue point here. Okay. What we can do by composing rotations that do exist in this picture is establish that the green points, which are the centers of all these triangles, must also be centers of threefold rotational symmetry. But again, bear in mind, we only have threefold symmetry, not sixfold. So the yellow and white triangles are not images of each other. under rotations. They are under translations. Sorry, they're not under translations either. The yellow ones are all images of each other, and the white ones. Okay, so we have this rotational symmetry represented by the original vertices and these green triangle centers. We may or may not also have reflections. So for example, if a reflection in this green line is a symmetry of the entire periodic pattern, which means the reflection in all the translates of that green lines would be as well, then because this is the threefold rotation center, the reflections in the other two green lines and all their translated copies must also be symmetries of the entire periodic pattern. But we can't have both this green line and this red line being axes of reflectional symmetry, because if we did, their composition would be a rotation through 60 degrees. And we're assuming that we don't have 60-degree rotations, only 120 degrees. So basically, the structure of reflectional symmetries in a picture like this can either be that each of the triangular tiles has all the symmetry of a triangle, so reflections in the three axes, or that they don't, but that the yellow tiles are images of the white ones under a reflection in the red lines. So either the three red lines are symmetry axes, or the three green ones are, or none of them are. But it can't be all six, because then we'd be back in the group P6M. Okay, so this way, we get three more groups. We get P3, which has only rotational symmetry. We get the one called P31M, which has reflections in the green lines. And we get P31M, which has reflections in the red lines, but not the green ones. And here are some origami patterns that realize those. And again, they're all derived from the original yellow one, really, the original one which has the whole symmetry of P6M. So this is a pattern that realizes the group P31M, P3N1. So we can see there that, again, here's our primitive cell. Each of the little triangular units has all the symmetry of a triangle, all the reflections and all the rotations. So this one on the left does, the highlighted one on the left, has all the symmetry of a triangle. Same for the one on the right, but they're not images of each other under a reflection. So this vertical line is not a reflection axis in this picture. This middle one has all the rotational symmetry. So this hexagon, this point, and this one are all centers of threefold rotational symmetry, but there are no reflections at all. So really it's obtained from that one, or this one, kind of by a process similar to what we had for the previous example, except that we kill off the sixfold rotational symmetry here by just kind of adjusting the region around a hexagon by sort of expanding some of the folds to create these three little sort of semicircular areas, which give us a threefold symmetry, but no longer sixfold. This one is actually the same piece of paper as that original yellow one with some adjustments to the folds. And it actually realizes the case P31M, where the sort of basic triangle here is a bit bigger. It's this region. It has the rotationals of a triangle, but it doesn't have any of the reflections of a triangle. But the two mirror versions of it are mirror images of each other. And this line is an axis of reflectional symmetry. So if I have 1 minute, maybe I'll just show you very quickly how, for example, we can obtain this picture, the one for this one from the yellow one. So I'll stop sharing that one again, if it's okay, and go back to the camera. So here we are back at our, so this is a copy of the yellow picture that we looked at. So if we want to change this one, so that instead of having all these triangles with the three hexagons, let's say as vertices, being images of each other under rotations and under reflections, but so that we have, let's say we take this primitive cell consisting of these four vertices. So if we want to adjust that so that the two triangles, the two parts of it, still retain all their symmetry, but that they're no longer mirror images of each other, this is a way of doing it. There's more than one way to do it, but this is a way to do it. If we just take this little guy, fold it over like that, and fold this one over, and fold that one over, then instead of this sort of thing with the three blocks in it, we have a little triangle over here. So adjust that one, leave that one the way it is, and that's how we go from that. So here's our triangle here, there it is. So yeah, and sort of adjust it so that these adjacent triangles are no longer mirror images of each other. And that, for example, is how we go from the yellow picture to this kind of brown one. And so it's a small adjustment, but it kind of moves us from one wallpaper group to another one. And we can think about how we're kind of adjusting the symmetries, how we're maintaining the threefold rotations, but killing off those axes of reflection that pass between two adjacent triangles. So that's what I have to say. I hope it's enough to give you a little bit of a flavor of what I was trying to do. And I'm so grateful again to all of you for being here, and to Martin and Milena for hosting and for organizing this wonderful, wonderful conference. Thank you so much, everybody.